Chapter 7, Question 1. Calculate the strength in grams per liter of 3NHCl and N/2 H2SO4 solutions. Strength of solution can be written as normality into equivalent weight. Now for HCl, the strength of solution will be normality of HCl is given as 3 and equivalent weight of HCl is 36.5. So this is equal to 109.5 grams per liter. Similarly, for H2SO4, strength of solution is equal to normality of H2SO4, that is 1/2, into equivalent weight of H2SO4, that is 49, and this is equal to 24.5 grams per liter. Question 2. How many milliliter of 1M sulfuric acid is required to neutralize 10 milliliter of 1M sodium hydroxide solution? The molarity of sulfuric acid is given as 1, molarity of sodium hydroxide is 1, and volume of sodium hydroxide is 10 milliliters. Now number of equivalents of sulfuric acid will be equal to number of equivalents of sodium hydroxide. Therefore, we can write N1 V1 is equal to N2 V2. Now, relationship between normality and molarity is normality is equal to molarity into valency factor. Therefore, we can write here N1 V1 can be written as M1 into valency factor into V1 is equal to M2 into valency factor into V2. M1 is the molarity of sulfuric acid, valency factor is the valency factor of sulfuric acid, and V1 is the volume of sulfuric acid, which is asked in the question. So putting the values, M1 is 1, valency factor of sulfuric acid is 2 because basicity of sulfuric acid is 2 into V1, and this is equal to M2 is the molarity of sodium hydroxide solution, that is 1, into valency factor of sodium hydroxide is 1 because acidity of sodium hydroxide is 1, into V2 of sodium hydroxide is given as, or volume of sodium hydroxide is given as 10. Solving this equation, the value for the volume of sulfuric acid is 5 milliliter. Question 3. 2 liters of ammonia at 13 degrees centigrade and 0.90 atmospheric pressure is neutralized by 134 milliliter of sulfuric acid solution. Find the normality of the acid. Moles of ammonia is equal to PV by RT. This is equal to pressure is 0.9 atmospheres, volume is 2 liters divided by R, the value of R is 0.0821 into temperature is 286 Kelvin. Solving this, the number of moles of ammonia is equal to 0.077 moles. Now equivalents of ammonia is equal to equivalents of sulfuric acid. Now equivalents of ammonia will be equal to moles of ammonia, that is 0.077 moles multiplied by valency factor of ammonia, that is 1. This is equal to equivalents of sulfuric acid. Equivalents of sulfuric acid will be equal to normality of sulfuric acid multiplied by volume of sulfuric acid, which is given as 134 milliliters, and the volume in liters will be 134 divided by 1000 liters. Solving this equation, the value for the normality of sulfuric acid is 0.57 N. Question 4. What weight of copper sulfate .5H2O must be taken to make 0.5 liter of 0.01 m copper 2 ion solution? Now weight of copper sulfate taken will be equal to molarity into volume. Molarity into volume gives the number of moles of copper sulfate, and multiplying this by the molecular weight of copper sulfate will give the weight of copper sulfate. So this is equal to, molarity is given as 0.01 m into volume is given as 0.5 liters, and molecular weight of CuSO4.5H2O is 249.55, and this is equal to 1.248 grams. Therefore, weight of CuSO4.5H2O is equal to 1.248 grams. Question 5, A part. Calculate the molarity of hydrogen chloride in a solution when 0.365 gram of it has been dissolved in 100 milliliter of the solution. B part. 3 gram of a salt of molecular weight 30 is dissolved in 250 gram of water. The molality of the solution is. Solving the A part, weight of hydrogen chloride is given as 0.365 gram. Dividing weight by molecular weight will give the number of moles of hydrogen chloride, and dividing the number of moles by volume of solution in liters will give the molarity of the solution. The volume is given in 100 milliliters, and this will be equal to 0.1 liters. Therefore, molarity of hydrogen chloride is equal to weight, that is 0.365, divided by molecular weight, that is 36.5, and dividing the number of moles by volume of solution in liters, that is 0.1 liters, gives the molarity of hydrogen chloride solution, and this is equal to 0.1 m. B part, weight of the salt is 3 grams, molecular weight of the salt is 30, and weight of water is 250 gram. So weight of water in kgs will be 0.25 kgs. Now molality of the solution will be equal to weight of the salt, that is 3 grams, divided by molecular weight of the salt, that is 30. This gives the moles of the salt, and dividing the moles of salt by the weight of water, that is 0.25 kgs, gives the molality of the solution, which is equal to 0.4 m. Question 6. Derive a formula for the volume of water V2 which must be added to V1 milliliter of concentrated solution of molarity M1 to give a solution of molarity M2. Volume of water is V2. Volume of the concentrated solution is V1, and molarity of the solution is M1, and the new solution will have the molarity M2. Now, if the volume of water is V2, then final volume of solution of molarity M2 will be equal to V1 plus V2. Now applying the formula, M1 V1 is equal to M2 into final volume. Now final volume is V1 plus V2. Therefore, M1 V1 is equal to M2 into V1 plus V2, and this is equal to M2 V1 plus M2 V2. Now rearranging this equation, we get M2 V2 is equal to M2 V1 minus M1 V1. Taking V1 common, this is equal to V1, and in bracket we get M2 minus M1. Therefore, V2 is equal to V1 into M2 minus M1 divided by M2. Question 7. Find the equivalent weight of H3PO4 in the reaction calcium hydroxide reacting with H3PO4 forming calcium hydrogen phosphate plus water. Now how many H plus ions are furnished by H3PO4? As can be seen from the reaction, only 2 H plus ions are furnished by H3PO4. Therefore, basicity of H3PO4 will be 2. And what is the formula for equivalent weight of acid? Equivalent weight of any acid is equal to molecular weight divided by its basicity. Therefore, equivalent weight of H3PO4 will be equal to molecular weight of H3PO4. Now, molecular weight of H3PO4 is 98 divided by basicity. Now, basicity of H3PO4 in this reaction is 2. So, 98 divided by 2, and this is equal to 49. Question 8. A 250 milliliter sample of 0.20 m hydrochloric acid is to be made by diluting the approximate amount of the concentrated reagent 11.7 m. What volume of the latter should be used? The basicity of hydrochloric acid is 1. Therefore, equivalent weight of hydrochloric acid will be same as the molecular weight, or the normality of hydrochloric acid will be same as the molarity, or we can also say that number of equivalents of hydrochloric acid will be same as the number of moles of hydrochloric acid. Now applying the formula M1V1 is equal to M2V2. Now M1 is the molarity of the original solution, that is 11.7, into V1. V1 is the volume that we have to find out, is equal to molarity of the new solution, that is 0.2, into V2, which is 250 milliliters. Solving this equation, we will get the volume V1 equals to 4.27 milliliters. Question 9. How many milliliter of each of two hydrochloric acids of strengths 12N and 3N are to be mixed to make 1 liter of 6N solution? The volume of the solution, which is formed by mixing of the hydrochloric acids of strength 12N and 3N, is 1 liter or 1000 milliliters. Let the volume of the hydrochloric acid of strength 12N be V milliliters. Therefore, volume of the hydrochloric acid of strength 3N will be 1000 minus V milliliters. Now multiplying normality and volume gives number of equivalents. But if the volume is in milliliters, then normality into volume in milliliters will give number of milliequivalents. Therefore, we can write 12 into V. This gives the milliequivalents of the hydrochloric acid of strength 12N plus 3 into 1000 minus V. This gives the milliequivalent of hydrochloric acid of strength 3N, and this will be equal to 6 into 1000. 6 into 1000 is the number of milliequivalents of hydrochloric acid in the final solution. Solving this equation, the value of V is equal to 333.33 milliliters. Therefore, volume of hydrochloric acid of strength 12N will be 333.33 milliliter. and volume of hydrochloric acid of strength 3N will be volume of HCl of strength 3N will be equal to 1000 minus 333.33, and this is equal to 666.67 milliliters. Question 10. What volumes of 2m and 6m solutions of HCl have to be mixed to prepare 500 milliliter of a 3m solution? Disregard the change in the volume in mixing. The total volume of the final solution is 500 milliliters. Let the volume of the 2m solution be V milliliters. Therefore, volume of the 6m solution will be 500 minus V milliliters. The basicity of HCl is 1. Therefore, molarity will be equal to normality, or number of milliequivalents will be equal to number of millimoles. Therefore, we can write 2 into V. 2 into V, or molarity into volume, gives the number of millimoles because the volume is in milliliters, plus 6 into 500 minus V is equal to 3 into 500. Solving this equation, we get the value of V. V is equal to 375 milliliter. Now this is the volume of the 2m solution of HCl. Therefore, volume of 6m solution of HCl is equal to 500 minus 375, and this is equal to 125 milliliters. Question 11. 1 liter of a solution contains 18.9 gram of HNO3 and 1 liter of another solution contains 3.2 gram of NaOH. In what volume ratio must these solutions be mixed to obtain a solution having a neutral reaction? Molecular weight of HNO3 is 63. Molecular weight of NaOH is 40. Since the reaction is neutral, equivalents of HNO3 will be equal to equivalents of NaOH. Now normality is equal to molarity into valency factor. Equivalents of HNO3 will be equal to 18.9 divided by 63 into 1 into volume of HNO3, let it be V1. 18.9 is the weight of HNO3. Dividing it by molecular weight of HNO3, that is 63, will give moles of HNO3, and moles of HNO3 divided by volume of solution given as 1 liter gives the molarity of HNO3. Multiplying the molarity by valency factor of HNO3, which is 1, and V1 gives the number of equivalents of HNO3, where V1 is the volume of HNO3. And this is equal to equivalents of NaOH. Equivalents of NaOH will be 3.2 divided by 40 into 1 into V2. 3.2 is the weight of NaOH, 40 is the molecular weight of NaOH, 1 is the volume of the solution of NaOH. Therefore, 3.2 divided by 40 gives the moles of NaOH, and dividing it by 1 gives the molarity of NaOH. Valency factor of NaOH is 1 and volume of NaOH is V2. Therefore, molarity into valency factor of NaOH into V2 gives the equivalents of NaOH. Solving this equation, we get V2 by V1 equals to 3.75 divided by 1, or this is also equal to 3.75:1. Question 12. 10 milliliter of sulfuric acid solution, specific gravity is equal to 1.84, contains 98% by weight of pure acid. Calculate the volume of 2.5 N NaOH solution required to just neutralize the acid. Specific gravity of sulfuric acid is the ratio of density of sulfuric acid to the density of water. Density of water is 1 gram per centimeter cube or 1 gram per milliliter. Therefore, specific gravity of sulfuric acid is also equal to the density of sulfuric acid, or we can say density of sulfuric acid is 1.84. Volume of sulfuric acid is given as 10 milliliter. Therefore, volume into density, that is 10 into 1.84, will give the weight of sulfuric acid. Now NaOH neutralizes sulfuric acid. Therefore, we can write equivalence of NaOH is equal to equivalence of sulfuric acid. Normality of NaOH is given as 2.5 N, and let the volume of NaOH required be V1. Therefore, equivalence of NaOH can be written as normality of NaOH into volume of NaOH, which is equal to equivalence of sulfuric acid. Equivalence of sulfuric acid can be written as weight of sulfuric acid divided by equivalent weight of sulfuric acid. Weight of sulfuric acid is equal to 10 into 1.84, but according to the question, only 98% of this weight is pure sulfuric acid. Therefore, weight of pure sulfuric acid will be 10 into 1.84 into 98 by 100. Equivalent weight of sulfuric acid is 49. Normality of NaOH is given as 2.5. Solving this equation, volume of NaOH or V1 is equal to 0.1472 liters, which is also equal to 147.2 milliliters. Question 13. What is the molarity and molality of a 13% solution by weight of sulfuric acid solution? Its density is 1.090 gram per milliliter. To what volume should 100 ml of this acid be diluted in order to prepare 1.5 N solution? The percentage by weight of sulfuric acid solution is 13%. This can be written as 13 by 100. 13 is the weight of sulfuric acid and 100 is the weight of solution. Density of the solution is given as 1.090 gram per milliliter. Therefore, volume of solution will be equal to weight of solution, that is 100, divided by density of solution, that is 1.090. Dividing this volume by 1000 gives the volume of solution in liters, and this is equal to 10 divided by 109 liters. Now molarity of sulfuric acid is equal to moles of sulfuric acid divided by volume of solution in liters. Now moles of sulfuric acid will be equal to weight of sulfuric acid, that is 13, divided by molecular weight of sulfuric acid, that is 98, and dividing the moles of sulfuric acid by volume of solution, that is 10 by 109. Solving this equation, we get molarity of sulfuric acid as 1.45 m. Molality of sulfuric acid is equal to moles of sulfuric acid divided by weight of solvent in kg. Now moles of sulfuric acid will be equal to weight of sulfuric acid, that is 13, divided by molecular weight of sulfuric acid, that is 98, and weight of solvent will be equal to weight of solution, that is 100, minus weight of solute, that is 13. This gives the weight of solvent in grams, and dividing it by 1000 will give the weight of solvent in kgs. Solving this equation, molality of sulfuric acid is equal to 1.52 m. Now the third part of this question, to what volume should 100 milliliter of this acid be diluted to prepare 1.5 n solution? For this, we apply the formula N1V1 is equal to N2V2. N1 is the normality of the original acid, and normality of the original acid is not given, but we know the molarity of the acid is 1.45 m. V1 is given as 100 milliliters and N2 is given as 1.5 n. Now N1 will be equal to molarity of sulfuric acid, which is 1.45, into valency factor of sulfuric acid, that is 2. Therefore N1V1 equals to N2V2 can be written as 1.45 into 2 into 100. Since the volume of solution is in milliliters, N1 into V1 gives the milli equivalents of sulfuric acid, and this is equal to 1.5 into V2. Solving this equation, V2 will be equal to 193.3 milliliters. Question 14. How many milliliter of concentrated sulfuric acid of a specific gravity 1.84 containing 98% sulfuric acid solution by weight is required to prepare 200 milliliter of 0.5 n solution? 98% sulfuric acid solution by weight means 98 by 100. 98 is the weight of sulfuric acid and 100 is the weight of solution. Therefore, volume of solution will be equal to weight divided by density, that is 100 divided by 1.84 milliliters, and this is also equal to 10 divided by 184 liters. Now applying the formula N1V1 is equal to N2V2. N1 is the normality of original solution, V1 is the volume of the solution which we have to find out, N2 is the normality of the final solution, that is 0.5, V2 is the volume of the final solution which is given as 200 milliliters. Now N1 will be equal to molarity M1 into valency factor of sulfuric acid. Molarity of sulfuric acid is equal to moles of sulfuric acid divided by volume of solution in liters, which is equal to 10 by 184 liters. Moles of sulfuric acid will be equal to weight of sulfuric acid, that is 98, divided by molecular weight of sulfuric acid, which is 98. Valency factor of sulfuric acid is 2. Now putting the value of normality N1 in this equation, we get 98 divided by 98 into 184 divided by 10 into 2 into volume V1, and this is equal to 0.5 into 200. Solving this equation, we get the value of V1 equals to 2.71 milliliters. Question 15. 26 milliliter of a 1N Na2CO3 solution is neutralized by the acids A and B in different experiments. The volumes of the acids A and B required were 10 milliliter and 40 milliliter respectively. How many volumes of A and B are to be mixed in order to prepare 1 liter of normal acid solution? Volume of sodium carbonate is 26 milliliter. Normality of sodium carbonate is 1. Normality into volume in milliliters will give milliequivalents of sodium carbonate. Now 26 milliequivalents of sodium carbonate is neutralized by 10 milliliters of acid A. Therefore, milliequivalents of sodium carbonate, that is 1 into 26, is equal to milliequivalents of A, that is normality of A. Let the normality of A be Na into volume of A, that is 10 milliliters. Solving this, we get normality of A equals to 2.6 N. Volume of B required to neutralize sodium carbonate is 40 milliliter. Therefore, we can write milliequivalents of sodium carbonate, that is 1 into 26 is equal to normality of B. Let the normality of B be NB into volume of B, that is 40 milliliters. Solving this, we get normality of B equals to 0.65 N. Now the second part of the question, how many volumes of A and B are to be mixed in order to prepare 1 liter of normal acid solution? So volume of the final acid solution is 1 liter or 1000 milliliter, and the normality of the final acid solution is 1. And let the volume of A be V1, volume of B be V2. Therefore, V1 plus V2 is equal to volume of the final acid solution, that is 1 liter or 1000 milliliters. From this we get volume of B or V2 equals to 1000 minus V1 milliliters. Now normality into volume of final acid solution, that is 1 into 1000 is equal to normality of A, that is 2.6, into volume of A, that is V1, plus normality of B, that is 0.65 N, into volume of B, that is 1000 minus V1 milliliters. Solving this equation, we get the value of V1 or volume of A equals to 179.4 milliliters, and volume of B or V2 equals to 1000 minus 179.4, which is equal to 820.6 milliliters. Question 16. 25 milliliter of a solution of Fe2 plus ions was titrated with a solution of the oxidizing agent Cr2O7 2-. 32.45 milliliter of 0.0153 m K2Cr2O7 solution was required. What is the molarity of the Fe2 plus solution? Now let the molarity of Fe2 plus ion solution be m. Volume of the solution is 25 milliliter and it is oxidized by Cr2O7 2-. Now when Fe2 plus ion is oxidized, it changes into Fe3 plus. The change in oxidation number is 1 and number of atoms of iron are 1. Therefore valency factor for iron is 1. Now for the oxidizing agent, Cr2O7 2- gets reduced to Cr3 plus. The change in oxidation number of chromium is 3 and number of atoms of chromium in Cr2O72- is 2. Therefore, total change in oxidation number is 3 into 2, that is 6. Therefore, valency factor is equal to 6. Now, normality is equal to molarity into valency factor. Now, for complete titration, milliequivalents of Fe2 plus is equal to milliequivalents of Cr2O7 2 minus. Milliequivalents of Fe2 plus will be equal to molarity of Fe2 plus ion solution, which is M, into valency factor, that is 1, into volume of Fe2 plus ion solution, given as 25 milliliters. And this is equal to milliequivalents of Cr2O7 2 minus. Milliequivalents of Cr2O7 2 minus will be equal to molarity of K2Cr2O7 solution given as 0.0153 m into valency factor, that is 6, into volume of K2Cr2O7 solution given as 32.45 milliliters. Now, solving this equation, molarity of Fe2 plus ion solution will be equal to 0.1192 m. Question 17. Upon heating a liter of a N/2 HCl solution, 2.675 gram of hydrogen chloride is lost and the volume of the solution shrinks to 750 milliliter. Calculate first the normality of the resultant solution, second the number of milliequivalents of HCl in 100 milliliter of the original solution. Volume of the original solution, let it be V1, is equal to 1 liter. Normality of the original solution, let it be N1, is equal to 1 by 2 N. Volume of the final solution is 750 milliliter. Now the first part of the question, calculate the normality of the resultant solution. Let the normality of the resultant solution be N2. Now weight of HCl in the original solution will be equal to normality of the original solution, that is 1 by 2, into volume of the original solution, that is 1 liter, into equivalent weight of HCl, that is 36.5, and this is equal to 18.25 gram. Now weight of HCl lost is equal to 2.675 gram. Therefore, weight of remaining HCl will be equal to 18.25 minus 2.675, and this is equal to 15.575 gram. The final volume of the solution is 750 milliliter, or V2 is equal to 750 divided by 1000 liters. Therefore, normality of the resultant solution, or N2, will be equal to number of equivalents of HCl divided by volume of solution in liters. Now, number of equivalents of HCl will be weight of HCl, that is 15.575 grams, divided by equivalent weight of HCl, that is 36.5, divided by volume of solution in liters, that is 750 divided by 1000. Solving this, normality of the resultant solution will be equal to 0.569 N. Now the second part of the question is calculate the number of milliequivalents of HCl in 100 milliliters of the original solution. Number of milliequivalents is equal to normality of the original solution, that is 1 by 2, into volume of the solution, which is given in the second part of the question as 100 milliliter, Therefore 1 by 2 into 100, and this is equal to 50 milli equivalents. Question 18. The reaction zinc plus copper sulfate forming copper plus zinc sulfate goes completely to the right. In one experiment, 10 gram of metallic zinc was added to 200 milliliter of copper sulfate solution. After all copper is precipitated, it was found that not all the zinc had dissolved. After filtration, the total solid at the end of the reaction was 9.810 gram. Calculate first the weight of copper deposited and second molarity of copper sulfate in the original solution. Atomic weight of copper is given as 63.5 and atomic weight of zinc is given as 65.4. The reaction is zinc plus copper sulfate forming copper plus zinc sulfate. When zinc changes to zinc sulfate, the change in oxidation number of zinc is 2 and the number of atoms of zinc is 1. Therefore, valency factor of zinc is 2. And in copper sulfate to copper, the change in oxidation number of copper is 2 and number of atoms of copper is 1. Therefore, valency factor of copper is 2. Now, according to the question, the weight of zinc is 10 gram. Now, let the weight of zinc which reacted with copper sulfate be x gram and weight of copper deposited be y gram. The weight of zinc which is left at the end of the reaction is 10 minus x gram. Now equivalents of zinc will be equal to equivalents of copper. Equivalents of zinc will be equal to weight of zinc, that is x gram, divided by equivalent weight of zinc. Now equivalent weight of zinc will be equal to atomic weight of zinc, that is 65.4, divided by valency factor of zinc, that is 2. And this is equal to equivalents of copper. Equivalents of copper will be weight of copper, that is y grams, divided by equivalent weight of copper. The equivalent weight of copper will be atomic weight of copper, that is 63.5, divided by valency factor of copper, that is 2, and this is equal to x by 65.4 equals to y by 63.5. As can be seen from this equation, x divided by 65.4 gives the moles of zinc and y divided by 63.5 gives the moles of copper. Since the equation is balanced and valency factor for zinc and copper are same, therefore it can also be said that moles of zinc is equal to moles of copper. Now from this equation, y is equal to x divided by 65.4 into 63.5. Therefore, weight of copper is equal to x divided by 65.4 into 63.5. Now, according to the question, the weight of zinc left, that is 10 minus x grams, plus the weight of copper formed, that is x divided by 65.4 into 63.5 is equal to 9.810 grams. Solving this equation, the value of x is equal to 6.54 grams. Now putting the value of x in equation 1, we get the value of y equals to 6.35 grams. Therefore, weight of copper formed in the reaction is 6.35 grams. Now in the second part of the question, we have to find the molarity of copper sulfate solution. As can be seen from the reaction, moles of copper is equal to moles of copper sulfate. Therefore, molarity of copper sulfate solution will be equal to moles of copper divided by volume of solution in liters. Moles of copper will be equal to weight of copper, that is 6.35 grams, divided by atomic weight of copper, that is 63.5, and moles of copper divided by volume of solution in liters. Now volume of solution is given as 200 milliliters. Therefore volume of solution in liters will be 200 divided by 1000 liters. Solving this equation, the molarity of copper sulfate solution is equal to 0.5 m. Question 19. 0.108 gram of finely divided copper was treated with an excess of ferric sulfate solution until copper was completely dissolved. The solution after the addition of excess dilute sulfuric acid required 33.7 milliliter of 0.1 N-KMnO4 for complete oxidation. Find the equation which represents the reaction between metallic copper and ferric sulfate solution. Atomic weight of copper is given as 63.6 and atomic weight of iron is given as 56. According to the question, copper reacts with ferric sulfate, that is Fe2SO4 whole thrice. The oxidation state of copper is 0 and the oxidation state of iron in ferric sulfate is +3. Copper will react with ferric sulfate, and in the product that is formed, copper will be present in some higher oxidation state, plus ferrous sulfate will be formed, which contains iron in lower oxidation state or +2 oxidation state. When this product is treated with H2SO4 and KMnO4 solution, that is, on addition of H2SO4 and KMnO4 solution to this product, since iron is present in lower oxidation state, ferrous sulfate will be oxidized by KMnO4 and iron will change into higher oxidation state, that is +3 oxidation state. Therefore, we can say that equivalents of KMnO4 will be equal to equivalents of FeSO4 and equivalents of FeSO4 is equal to equivalents of copper. Therefore, we can write equivalents of copper is equal to equivalents of KMnO4. Now equivalents of copper will be equal to weight of copper, that is 0.108 grams divided by equivalent weight of copper. Equivalent weight of copper will be equal to atomic weight of copper, that is 63.6 divided by valency factor of copper, and this is equal to equivalents of KMnO4. Equivalents of KMnO4 will be equal to normality of KMnO4, that is 0.1 into volume of KMnO4 solution in liters, that is 33.7 divided by 1000 liters. Solving this equation, we get the valency factor of copper equals to 2. Therefore, in the product formed, the oxidation state of copper is +2. Therefore, the reaction can be written as copper plus Fe2SO4 whole thrice forming CuSO4 plus FeSO4. And to balance the equation, copper plus Fe2SO4 whole thrice forming CuSO4 plus 2FeSO4. Question 20. A commercial sample 2.013 gram of NaOH containing Na2CO3 as an impurity was dissolved to give 250 milliliter of solution. A 10 ml portion of the solution required 20 ml of 0.1 NH2SO4 solution for complete neutralization. Calculate the percentage by weight of Na2CO3 in the sample. Let the weight of NaOH be x gram and therefore the weight of Na2CO3 will be 2.013 minus x gram. Now for NaOH, equivalents of NaOH in 250 milliliters of the solution is equal to x by 40 equivalents, or it can also be written as milli-equivalents of NaOH in 250 milliliters of solution is equal to x by 40 into 1000 milli-equivalent. Therefore, milli-equivalents of NaOH in 10 milliliter of solution is equal to x by 40 into 1000 divided by 250 into 10, and this is equal to x milli-equivalents. Similarly, for Na2CO3, equivalents of Na2CO3 in 250 milliliters of solution is equal to 2.013 minus x divided by 53 equivalents, or milli-equivalents of Na2CO3 in 250 milliliters is equal to 2.013 minus x divided by 53 into 1000 milli-equivalents. Therefore, milli-equivalents of Na2CO3 in 10 ml of solution is equal to 2.013 minus x divided by 53 into 1000 divided by 250 into 10 milli-equivalents. This is equal to 2.013 minus x divided by 53 into 40 milli-equivalents. Now milli-equivalents of sodium hydroxide, that is x, plus milli-equivalents of sodium carbonate, that is 2.013 minus x divided by 53 into 40 is equal to milli-equivalents of sulfuric acid required for complete neutralization. And milli-equivalents of sulfuric acid will be equal to normality of sulfuric acid, that is 0.1, into volume of solution in milliliters, that is 20 milliliters. Solving this equation, the value of x is equal to 1.963 grams. Therefore, weight of NaOH is equal to 1.963 grams, and weight of sodium carbonate will be equal to 2.013 minus 1.963, which is equal to 0.05 grams. Therefore, percentage of sodium carbonate will be equal to 0.05 divided by 2.013 into 100, and this is equal to 2.48%. Question 21. A solution of a mixture of KCl and KOH was neutralized with 120 milliliter of 0.12 NHCl. Calculate the amount of KOH in the mixture. After titration, the resultant solution was made acidic with HNO3. Then excess of AgNO3 was added to precipitate the AgCl, which weighed 3.7 gram after drying. Calculate percentage of KOH in the original mixture. When HCl is added to a mixture of KCl and KOH, only KOH reacts with HCl to form KCl. The reaction is KOH plus HCl forming KCl plus H2O. Milli-equivalents of HCl will be equal to milli-equivalents of KOH, which will be equal to milli-equivalents of KCl. Or we can also say that milli-equivalents of KCl will be equal to milli-equivalents of HCl, and this is equal to milli-equivalents of HCl will be equal to normality of HCl, that is 0.12 N, into volume of HCl in milliliters, that is 120 milliliters, and this is equal to 14.4 milli equivalents. Now milli equivalents of KCl is equal to milli equivalents of KOH, and this is equal to 14.4 milli equivalents. Therefore, weight of KOH will be equal to equivalents of KOH, that is 14.4 divided by 1000 into equivalent weight of KOH, which is 56, and this is equal to 0.8064 grams. Similarly, weight of KCl formed will be equal to equivalents of KCl, that is 14.4 divided by 1000 into equivalent weight of KCl, that is 74.5, and this is equal to 1.0728 grams. Now when excess of AgNO3 was added, the AgNO3 reacts with KCl to form AgCl. The reaction will be KCl plus AgNO3 forming AgCl plus KNO3. Now weight of AgCl formed is 3.7 grams. Therefore, equivalents of AgCl formed is 3.7 divided by equivalent weight of AgCl, that is 143.5, and equivalents of AgCl will be equal to equivalents of KCl. Now this KCl includes the KCl which is present originally as well as the KCl which is formed from KOH. Therefore, total weight of KCl will be equal to equivalents of KCl, that is 3.7 divided by 143.5 into equivalent weight of KCl, that is 74.5, and this is equal to 1.921 grams. Now weight of KCl present originally will be equal to total weight of KCl, that is 1.921 grams, minus weight of KCl formed from KOH, that is 1.0728 grams, and this is equal to 0.8482 grams. Therefore, weight of KCl present originally plus weight of KOH is equal to 0.8482 grams plus 0.8064 grams, and this is equal to 1.6546 grams. Therefore, percentage of KOH is equal to weight of KOH, that is 0.8064 grams, divided by total weight of KCl and KOH present, that is 1.6546 gram into 100, and this is equal to 48.7%. Question 22. 10.03 gram of vinegar was diluted to 100 milliliter and a 25 ml sample was titrated with the 0.0176 m of barium hydroxide solution. 34.30 milliliter was required for equivalence. What is the percent of acetic acid in the vinegar? Milli equivalents of acetic acid will be equal to milli equivalents of barium hydroxide, and this is equal to molarity of barium hydroxide, that is 0.0176, into volume of barium hydroxide, that is 34.30 milliliters, into valency factor of barium hydroxide, that is 2, and this is equal to 1.207 milliequivalents. Therefore, milliequivalents of acetic acid is equal to 1.207 milliequivalents. Now 25 milliliters of acetic acid contains 1.207 milliequivalents. Therefore, 100 milliliter of acetic acid will contain 1.207 divided by 25 into 100, and this is equal to 4.828 milliequivalents, or this is also equal to 4.828 divided by 1000 equivalents of acetic acid. Therefore, weight of acetic acid is equal to equivalents of acetic acid, that is 4.828 divided by 1000 into equivalent weight of acetic acid, that is 60, and this is equal to 0.289 grams. Therefore, percentage of acetic acid is equal to weight of acetic acid, that is 0.289 gram, divided by weight of vinegar, that is 10.03 grams, into 100, and this is equal to 2.9%. Question 23. Zinc can be determined volumetrically by the precipitation reaction. This is the reaction which is given. A sample of zinc ore weighing 1.432 gram was prepared for reaction and required 34.68 milliliters of 0.1043 m K4FeCN6 for titration. What is the percentage of zinc in the ore? Now, zinc present in the ore reacts with K4FeCN6, and as can be seen from the balanced equation, 3 moles of zinc reacts with 2 moles of K4FeCN6. Therefore, the ratio of moles of zinc to moles of K4FeCN6 is 3 by 2. Or we can also write 3 by 2 is equal to moles of zinc divided by moles of K4FeCN6. Now, moles of zinc can also be written as weight of zinc divided by atomic weight of zinc, that is 65.4, and moles of K4FeCN6 will be equal to molarity of K4FeCN6, that is 0.1043, into volume of K4FeCN6, that is 34.68 milliliters, or 34.68 divided by 1000 liters. Solving this equation, we get weight of zinc equals to 0.3548 grams. Therefore, percentage of zinc present in the ore is weight of zinc, that is 0.3548 grams, divided by weight of ore, that is 1.5432 grams, into 100, and this is equal to 23%. Question 24. 5.5 gram of a mixture of FeSO4.7H2O and Fe2SO4 whole thrice .9H2O requires 5.4 milliliter of 0.1 N KMnO4 solution for complete oxidation. Calculate the number of mole of hydrated ferric sulfate in the mixture. The oxidation number of iron in FeSO4 7H2O is +2, and the oxidation number of iron in Fe2SO4 whole thrice .9H2O is plus 3. Therefore, KMnO4 will oxidize the iron present in FeSO4.7H2O from plus 2 oxidation state to plus 3 oxidation state. Therefore, we can write equivalents of FeSO4.7H2O is equal to equivalents of KMnO4 solution. Now, equivalents of KMnO4 solution will be equal to normality of KMnO4 solution, that is 0.1 N, into volume of KMnO4 solution in liters, that is 5.4 divided by 1000 liters, and this is equal to 0.54 divided by 1000 equivalents of KMnO4 or 0.54 divided by 1000 equivalents of FeSO4.7H2O. Therefore, weight of FeSO4.7H2O is equal to equivalents of FeSO4.7H2O, that is 0.54 divided by 1000 into equivalent weight of FeSO4.7H2O, which in this case is 278, and this is equal to 0.150 grams. Therefore, weight of FeSO4.7H2O is 0.150 grams. Therefore, weight of Fe2SO4 whole thrice dot 9H2O is equal to weight of the mixture, that is 5.5 gram, minus weight of FeSO4.7H2O, that is 0.150 grams, and this is equal to 5.35 grams. Therefore, moles of Fe2SO4 whole thrice dot 9H2O is equal to weight of Fe2SO4 whole thrice dot 9H2O, that is 5.35 grams, divided by molecular weight of hydrated ferric sulfate, that is 562, and this is equal to 0.0095 moles. Question 25. A chemist is preparing to analyze samples that will contain no more than 0.5 gram of uranium. His procedure calls for preparing the uranium as U4 plus ion and oxidizing it by MnO4 minus in acid solution. The reaction is given as 5U4 plus 2MnO4 minus plus 6H2O forming 5UO2 plus 2Mn2 plus 4H3O plus. If he wants to react the total U4 plus sample with a maximum of 50 milliliter of KMnO4 solution, what concentration should he choose? Now, as can be seen from the balanced equation, 5 moles of U4 plus ion reacts with 2 moles of MnO4 minus ion. Therefore, the ratio of the moles of U4 plus ion to moles of MnO4 minus ion or moles of KMnO4 solution will be equal to 5 by 2, or we can also say 5 by 2 is equal to moles of U4 plus ion divided by moles of KMnO4 solution. Now, moles of U4 plus ion is equal to weight of uranium, which is given as 0.5 gram, divided by atomic weight of uranium, that is 238, and moles of KMnO4 solution will be equal to molarity of KMnO4 solution, let it be M, into volume of KMnO4 solution in liters, that is 50 divided by 1000 liters. Solving this equation, the value for the molarity of KMnO4 solution will be equal to 0.0168 m. Question 26. For the standardization of a barium hydroxide solution, 0.2 gram of potassium acid phthalate, weight of 1 mole is equal to 204.2 gram, was weight which was then titrated with barium hydroxide solution. The titration indicated equivalence at 27.80 milliliter of barium hydroxide solution. What is the molarity of the base? This is the equation for the reaction. Now, as can be seen from the balanced equation, 2 moles of potassium acid phthalate reacts with 1 mole of barium hydroxide solution, or the ratio of moles of potassium acid phthalate to moles of barium hydroxide solution is 2:1, or we can also write 2 by 1 is equal to moles of KHC8H4O4 divided by moles of barium hydroxide solution. Now, moles of potassium acid phthalate is equal to weight of potassium acid phthalate, which is given as 0.2 gram, divided by molecular weight of potassium acid phthalate, which is 204.2 gram. Moles of barium hydroxide is equal to molarity of barium hydroxide solution, let it be M, into volume of barium hydroxide solution in liters, which is equal to 27.80 divided by 1000 liters. Solving this equation, the value for molarity of barium hydroxide solution is equal to 0.0176 m. Question 27. A sample of magnesium metal containing some magnesium oxide as impurity was dissolved in 125 milliliter of 0.1 NH2SO4. The volume of hydrogen evolved at 27.3 degrees centigrade and 1 atmosphere was 120.1 milliliter. The resulting solution was found to be 0.02 N with respect to H2SO4. Calculate first the weight of the sample dissolved and second the percentage by weight of magnesium in the sample. Neglect any change in the volume of the solution. The volume of H2SO4 is 125 milliliter and normality of H2SO4 solution is 0.1 N. The equation for the reaction is magnesium plus H2SO4 forming magnesium sulfate plus hydrogen gas is evolved, and magnesium oxide also reacts with H2SO4 forming magnesium sulfate plus H2O. Now, equivalents of H2SO4 present is equal to normality of H2SO4, that is 0.1 N, into volume of H2SO4 in liters, that is 125 divided by 1000, and this is equal to 0.0125 equivalents. Equivalents of H2SO4 left is equal to normality of H2SO4, that is 0.02 N, into volume of H2SO4 solution, that is 125 divided by 1000 liters, and this is equal to 0.0025 equivalents. Therefore, equivalents of H2SO4 reacted is equal to equivalents of H2SO4 present, that is 0.0125 equivalents, minus equivalents of H2SO4 left, that is 0.0025, and this is equal to 0.01 equivalents. Now, applying the equation, P1 V1 by T1 is equal to P2 V2 by T2, where P1 is the given pressure, V1 is the given volume, and T1 is the given temperature. and P2, V2 and T2 are pressure, volume and temperature at standard conditions. Therefore, P1 is given as 1 atmosphere, V1 is given as 120.1 milliliter, T1 is given as 300.3 Kelvin, P2 is 1 atmosphere, T2 is 273 Kelvin. Solving this equation, we get the volume of hydrogen, that is V2 is equal to 109.2 milliliters. This is the volume of hydrogen evolved when magnesium reacts with sulfuric acid. Now equivalence of magnesium is equal to equivalence of hydrogen. Equivalence of magnesium will be equal to weight of magnesium divided by equivalent weight of magnesium, which is 24.3 divided by 2, where 24.3 is the atomic weight of magnesium and 2 is the valency factor, and this is equal to equivalence of hydrogen. Equivalence of hydrogen will be equal to volume of hydrogen evolved, that is 109.2 milliliters, divided by equivalent volume of hydrogen, that is 11,200 milliliters. Solving this equation, we get weight of magnesium equals to 0.1185 gram, and from this same equation we get equivalence of magnesium equals to 0.00975 equivalents. Now equivalence of magnesium plus equivalence of magnesium oxide is equal to equivalence of sulfuric acid reacted, and this is equal to 0.01 equivalents. Therefore, from this equation, we get equivalence of magnesium oxide equals to 0.01 minus equivalence of magnesium, which is equal to 0.00975, and this is equal to 0.00025 equivalents. Therefore, weight of magnesium oxide is equal to equivalence of magnesium oxide, that is 0.00025 into equivalent weight of magnesium oxide, that is 20, and this is equal to 0.005 grams. Therefore, total weight of magnesium plus magnesium oxide is equal to 0.1185 grams plus 0.005 grams, and this is equal to 0.1235 grams. Therefore, percentage of magnesium is equal to weight of magnesium, that is 0.1185 gram, divided by total weight of magnesium and magnesium oxide, that is 0.1235 gram into 100, and this is equal to 95.95%. Question 28. A piece of aluminium weighing 2.7 gram is treated with 75 milliliter of H2SO4, specific gravity 1.18, containing 24.7% H2SO4 by weight. After the metal is completely dissolved, the solution is diluted to 400 milliliter. Calculate the molarity of free sulfuric acid in the resulting solution. Equivalence of sulfuric acid is equal to weight of sulfuric acid, that is 24.7, divided by equivalent weight of sulfuric acid, that is 49. Volume of solution is equal to mass by density, which is equal to 100 divided by 1.18 milliliters, and volume of solution in liters will be 100 by 1.18 divided by 1000 liters. Now equivalence of aluminium is equal to equivalence of sulfuric acid. which is equal to weight of aluminium, that is 2.7 gram, divided by equivalent weight of aluminium, which is equal to 27 by 3. 27 is the atomic weight of aluminium and 3 is the valency factor, and this is equal to 0.3 equivalents. Therefore, equivalence of sulfuric acid that reacted with aluminium is 0.3 equivalents. Now, equivalence of sulfuric acid present is equal to normality of sulfuric acid solution into volume of sulfuric acid, which is 75 by 1000 liters. Normality of sulfuric acid will be equal to equivalence of sulfuric acid, that is 24.7 divided by 49, divided by volume of solution in liters, that is 1 by 1.18 into 10 liters. Therefore, equivalent of sulfuric acid present is equal to normality of sulfuric acid, that is equal to 24.7 divided by 49 into 1.18 into 10 into volume of sulfuric acid in liters, that is 75 divided by 1000 liters, and this is equal to 0.446 equivalents. Out of this 0.446 equivalents of sulfuric acid present, 0.3 equivalents of sulfuric acid reacted with aluminium. Therefore, equivalents of sulfuric acid left is equal to 0.446 equivalents minus 0.3 equivalents, and this is equal to 0.146 equivalents. Therefore, molarity of sulfuric acid solution is equal to normality of sulfuric acid divided by valency factor, that is 2, and normality of sulfuric acid is equal to equivalence of sulfuric acid left, that is 0.146 divided by volume of the solution. Now, according to the question, after the metal is completely dissolved, the solution is diluted to 400 milliliter. Therefore, volume of solution will be 0.4 liters. Therefore, normality of sulfuric acid will be 0.146 divided by 0.4, where 0.146 is the equivalence of sulfuric acid left and 0.4 liters is the volume of solution. Solving this, the molarity of sulfuric acid is equal to 0.18 m. Question 29. 4 gram of mixture of sodium chloride and sodium carbonate was dissolved in water and the volume made up to 250 milliliter. 25 milliliter of this solution required 50 milliliter of N by 10 HCl for complete neutralization. Calculate percentage composition of the original mixture. Let the weight of sodium carbonate be W grams. Therefore, weight of NaCl will be 4 minus W grams. Now, out of NaCl and Na2CO3, only Na2CO3 will react with HCl. The reaction will be Na2CO3 plus HCl forming NaCl plus H2O plus CO2. Now, equivalent weight of sodium carbonate is molecular weight of sodium carbonate, that is 106, divided by valency factor of sodium carbonate, that is 2, and this is equal to 53. Now, equivalence of sodium carbonate in 250 milliliter of solution is equal to W by 53 equivalents. Therefore, equivalence of sodium carbonate in 25 milliliter of solution will be equal to W by 53 into 25 divided by 250, and this is equal to W by 53 into 10 equivalents. Now, equivalence of sodium carbonate in 25 milliliter of solution will be equal to equivalence of HCl. Therefore, we can write W by 53 into 10 is equal to equivalence of HCl. Now equivalence of HCl will be equal to normality of HCl, that is 1 by 10, into volume of HCl in liters, that is 50 divided by 1000 liters. Solving this, the value for W is equal to 2.65 grams. Therefore, percentage of sodium carbonate is equal to weight of sodium carbonate, that is 2.65 gram, divided by total weight of the mixture of sodium chloride and sodium carbonate, that is 4 gram, into 100, and this is equal to 66.25%. Therefore, percentage of sodium chloride in the mixture is equal to 100 minus 66.25, and this is equal to 33.75%. Question 30. 1 gram of a mixture consisting of equal number of moles of carbonates of the two univalent metals required 44.4 milliliter of 0.5 N HCl for complete reaction. If the atomic weight of one of the metals is 7, find the atomic weight of the other metal. What will be the total amount of sulfate formed on gravimetric conversion of 1 gram of the mixture of sulfates? Let the molecular formula of one of the carbonates be M2CO3 and the other carbonate be M-2CO3, where M and M- are the two metals. Now both the metals are univalent and the number of moles of carbonate is same. Let the weight of M2CO3 be x grams. Therefore, weight of M-2CO3 will be 1 minus x grams. Therefore, moles of M2CO3 will be weight of M2CO3, that is x, divided by molecular weight of M2CO3, that is 74, and moles of M-2CO3 will be 1 minus x divided by molecular weight of M-2CO3. Now atomic weight of the metal M- is not given. Let it be Y. Therefore, molecular weight of M-2CO3 will be 2Y plus 60. 60 is the weight of carbonate ion. Now number of moles of carbonates is the same. The valency factor for the carbonates is same. Therefore, equivalence of the two carbonates is also same. Equivalence of M2CO3 will be weight of M2CO3, that is x, divided by equivalent weight of M2CO3, that is 74 divided by 2. 74 is the molecular weight of M2CO3 and 2 is the valency factor. Similarly, equivalence of M-2CO3 will be weight of M-2CO3, that is 1 minus x, divided by equivalent weight of M-2CO3, that is 2y plus 60 divided by 2, where 2y plus 60 is the molecular weight of M-2CO3 and 2 is the valency factor. Since the number of moles of the two carbonates is same and number of equivalents of two carbonates is also same, therefore we can write equivalence of M2CO3, that is x divided by 74 by 2, plus equivalence of M-2CO3. We can write equivalence of M-2CO3 also as x divided by 74 by 2, and this is equal to equivalence of HCl required for complete reaction, which is equal to normality of HCl, that is 0.5 N, into volume of HCl in liters, that is 44.4 divided by 1000 liters. Solving this equation, the value for x is equal to 0.41 grams. Therefore, weight of M2CO3 in the mixture is 0.41 grams and weight of M-2CO3 in the mixture will be 1 minus x gram, which is equal to 1 minus 0.41, which is equal to 0.59 grams. Now substituting the value of x and 1 minus x, we can write moles of M2CO3, that is 0.41 divided by 74 is equal to 0.59 divided by 2y plus 60, and solving this equation, the value for y is equal to 23.2. Therefore, atomic weight of m dash is equal to 23.2. Now both the carbonates get converted into sulfate, that is M2CO3 converts to M2SO4. Let the weight of sulfate be W1 gram. The equivalent of carbonate is equal to equivalence of sulfate. Therefore, we can write equivalence of M2CO3 equals to equivalence of M2SO4. Now, equivalence of M2CO3 will be equal to weight of M2CO3, that is 0.41 gram, divided by equivalent weight of M2CO3, that is 74 by 2, and this is equal to equivalence of M2SO4, which is equal to weight of M2SO4, that is W1, divided by equivalent weight of M2SO4, that is 110 by 2. 110 is the molecular weight of M2SO4 and 2 is the valency factor. Solving this, the value for W1 is equal to 0.609 gram. Similarly, M-2CO3 converts to M-2SO4. Let the weight of M-2SO4 be W2 grams. Now equivalence of M-2CO3 is equal to equivalence of M-2SO4. Therefore, we can write weight of M-2CO3, that is 0.59 grams, divided by equivalent weight of M-2CO3, that is 106.4 divided by 2, where 106.4 is the molecular weight of M-2CO3 and 2 is the valency factor, and this is equal to equivalence of M-2SO4. The equivalence of M-2SO4 will be equal to weight of M-2SO4, that is W2 grams, divided by equivalent weight of M-2SO4. Equivalent weight of M-2SO4 will be molecular weight of M-2SO4, that is 142.4 divided by valency factor, that is 2. Solving this equation, the value for W2 will be equal to 0.789 gram. Therefore, the total weight of the sulfate will be equal to W1 plus W2, and this is equal to 0.609 plus 0.789, and this is equal to approximately 1.4 gram. Question 31. A mixture containing only sodium carbonate and potassium carbonate weighing 1.22 gram was dissolved in water to form 100 milliliter of a solution. 20 milliliter of this solution required 40 milliliter of 0.1 NaHCl for neutralization. Calculate the weight of sodium carbonate in the mixture. If another 20 milliliter portion of the solution is heated with excess of barium chloride, what will be the weight of the precipitate obtained? Now both sodium carbonate and potassium carbonate will react with HCl. The reaction can be written as Na2CO3 plus K2CO3 plus HCl, forming NaCl plus KCl plus H2O plus CO2. Let the weight of sodium carbonate be X gram and weight of potassium carbonate will be 1.22 minus X gram. Now 100 milliliter solution of the mixture contains X by 53 equivalents of sodium carbonate, where X is the weight of sodium carbonate and 53 is the equivalent weight of sodium carbonate. Therefore, 20 milliliter of the solution will contain X by 53 into 20 by 100 and this is equal to x by 53 into 5 equivalents. Similarly, 100 milliliter of solution contains 1.22 minus x divided by 69 equivalents of potassium carbonate, where 1.22 minus x is the weight of potassium carbonate and 69 is the equivalent weight of potassium carbonate. Therefore, 20 milliliter of the solution will contain 1.22 minus x divided by 69 into 20 by 100 equivalents of potassium carbonate, and this is equal to 1.22 minus x divided by 69 into 5 equivalents of potassium carbonate. Since both sodium carbonate and potassium carbonate react with HCl, therefore equivalents of sodium carbonate plus equivalents of potassium carbonate will be equal to equivalents of HCl, and this is equal to x by 53 into 5 plus 1.22 minus x divided by 69 into 5 equals to equivalents of HCl. Equivalents of HCl is equal to normality of HCl, that is 0.1 n, into volume of HCl in liters, which is equal to 40 divided by 1000 liters. Solving this equation, the value for x is equal to 0.53 grams. Therefore, weight of sodium carbonate in the mixture is 0.53 grams and weight of potassium carbonate in the mixture will be 1.22 minus x grams, and this is equal to 1.22 minus 0.53, and this is equal to 0.69 grams. Now 20 milliliter portion of the solution was heated with excess barium chloride. Now on heating with excess barium chloride, both sodium carbonate and potassium carbonate react with barium chloride, and the product contains precipitate of barium carbonate. Therefore, we can write equivalents of sodium carbonate in 20 milliliter of the solution plus equivalents of potassium carbonate in 20 milliliter of the solution is equal to equivalents of barium carbonate. Now, equivalents of sodium carbonate in 20 milliliter of solution is weight of sodium carbonate, that is 0.53 divided by 53 into 5 plus equivalents of potassium carbonate in 20 milliliter solution is weight of potassium carbonate, that is 0.69 divided by 69 into 5, and this is equal to equivalents of barium carbonate. Now equivalents of barium carbonate will be equal to weight of barium carbonate divided by equivalent weight of barium carbonate. Equivalent weight of barium carbonate is molecular weight of barium carbonate, that is 197 divided by valency factor of barium carbonate, that is 2. Solving this equation, weight of barium carbonate or the weight of the precipitate of barium carbonate formed is equal to 0.394 grams. Question 32. 1 gram of a moist sample of a mixture of KCl and KClO3 was dissolved in water and made up to 250 milliliter. 25 milliliter of this solution was treated with sulfur dioxide to reduce the chlorate to chloride, and excess sulfur dioxide was removed by boiling. The total chloride was precipitated as silver chloride. The weight of the precipitate was 0.1435 gram. In another experiment, 25 milliliter of the original solution was heated with 30 milliliter of 0.2N solution of ferrous sulfate and unreacted ferrous sulfate required 37.5 milliliter of 0.08N solution of an oxidizing agent for complete oxidation. Calculate the molar ratio of chlorate to chloride in the given mixture. Fe2 plus reacts with ClO3 minus according to the reaction ClO3 minus plus 6Fe2 plus 6H plus forming Cl minus plus 6Fe3 plus 3H2O. Now from this equation, it can be seen that the valency factor of chlorate is 6. Now in the second experiment, where chlorate ion is heated with ferrous sulfate, the equivalence of chlorate will be equal to equivalent of ferrous sulfate that took part in the reaction. And equivalent of ferrous sulfate that took part in the reaction will be equivalent of ferrous sulfate present initially, which is equal to normality of ferrous sulfate, that is 0.2N, into volume of ferrous sulfate in liters, that is 30 divided by 1000 liters, minus equivalence of ferrous sulfate left after the reaction. Now equivalence of ferrous sulfate that is left after the reaction or unreacted ferrous sulfate according to the question required 37.5 milliliter of 0.08N solution of an oxidizing agent for complete oxidation. Therefore, equivalence of ferrous sulfate that did not take part in the reaction will be equal to the equivalence of the oxidizing agent required for complete oxidation, and that is equal to normality of the oxidizing agent, which is equal to 0.08 N into volume of the oxidizing agent in liters, that is 37.5 divided by 1000 liters, and this is equal to 3 divided by 1000 equivalents. Therefore, equivalence of chlorate is equal to equivalence of ferrous sulfate that took part in the reaction, and that took part in the reaction, and it is equal to 3 by 1000 equivalents. Therefore, moles of chlorate will be equal to equivalence of chlorate, that is 3 divided by 1000 divided by valency factor of chlorate, that is 6, and this is equal to 0.5 into 10 to the power minus 3 moles. Now in the first part of the experiment, the mixture of potassium chloride and potassium chlorate was treated with sulfur dioxide. Now on treatment with sulfur dioxide, chlorate ion got reduced to chloride ion. The chlorate ion got reduced to chloride ion on treatment with sulfur dioxide. Now after converting the chlorate to chloride, the total chloride was precipitated as silver chloride. Now this total chloride includes the chloride from potassium chloride and the chloride which is obtained from chlorate or potassium chlorate. Now applying principle of atom conservation to chlorine atoms, we can write moles of KCl plus moles of KClO3 is equal to moles of AgCl. Therefore, moles of KCl plus moles of KClO3 is 0.5 into 10 to the power minus 3 moles, and this is equal to moles of AgCl. Moles of AgCl will be equal to weight of AgCl, that is 0.1435 grams, divided by molecular weight of AgCl, that is 143.5, and this is equal to 0.001 moles. From this, moles of KCl is equal to 0.5 into 10 to the power minus 3 moles. Therefore, moles of KCl, or the ratio of moles of KCl to moles of KClO3 is equal to 1:1. Question 33. 0.6 gram of a sample of pyrolusite was boiled with 200 milliliter of N by 10 oxalic acid and excess of dilute sulfuric acid. The liquid was filtered and residue washed. The filtrate and washings were mixed and made up to 500 milliliter. 100 milliliter of this solution required 50 milliliter of N by 30 KMnO4 solution. Calculate the percentage of MnO2 in the given sample of pyrolusite. Now, pyrolusite is oxide ore of manganese having the chemical formula MnO2. In MnO2, the oxidation state of manganese is +4. Now, on treatment with oxalic acid, that is H2C2O4, and sulfuric acid, that is H2SO4, it forms compound containing manganese in +2 oxidation state. Therefore, change in oxidation number of manganese is 2 and number of manganese atoms in MnO2 is 1. Therefore, valency factor of MnO2 is 2. Let the weight of MnO2 that reacted with oxalic acid be x grams. Therefore, equivalence of MnO2 that reacted with oxalic acid is x divided by equivalent weight of MnO2. Equivalent weight of MnO2 will be molecular weight of MnO2, that is 87, divided by valency factor of MnO2, that is 2. Now, equivalence of oxalic acid present is equal to normality of oxalic acid, that is 1 by 10, into volume of oxalic acid in liters, that is 200 by 1000 liters, and this is equal to 0.02 equivalents. Now, equivalence of oxalic acid that reacted with MnO2 is equal to equivalence of MnO2. Therefore, we can write equivalence of oxalic acid reacted is equal to equivalence of MnO2, and this is equal to x divided by 87 by 2. Therefore, equivalence of oxalic acid left is equal to equivalence of oxalic acid present, that is 0.02 equivalents, minus equivalence of oxalic acid reacted, that is x divided by 87 by 2, and this is equal to 1.74 minus 2x divided by 87. Now, according to the question, the filtrate and washings were mixed and made up to 500 milliliter. Therefore, 500 milliliters of filtrate and washings contained 1.74 minus 2x divided by 87 equivalents of oxalic acid. Therefore, 100 milliliters of the filtrate will contain 1.74 minus 2x divided by 87 into 100 by 500 equivalents of oxalic acid, and this is equal to 1.74 minus 2x divided by 435 equivalents. Now, this 100 ml solution required 50 milliliter of N by 30 KMnO4 solution. Therefore, equivalence of oxalic acid in 100 ml solution, that is 1.74 minus 2x divided by 435 is equal to equivalence of KMnO4, that is normality of KMnO4. Normality of KMnO4 is 1 by 30 into volume of KMnO4 solution in liters, that is 50 divided by 1000 liters. Solving this, the value of x is equal to 0.5075 grams. Therefore, percentage of MnO2 is equal to 0.5075 grams divided by 0.6 grams into 100, and this is equal to 84.58%. Question 34. 25 milliliter of 0.107 m H3PO4 was titrated with a 0.11 m solution of a NaOH solution to the endpoint identified by the color change of the indicator bromocresol green. This required 23.1 milliliter. The titration was repeated using phenolphthalein indicator. This time 25 milliliter of 0.107 m H3PO4 required 46.8 milliliter of the 0.115 m NaOH. What is the coefficient N in the equation? H3PO4 plus NOH minus forming NH2O plus H3 minus NPO4 whole N minus for each reaction. Now in this question, when the titration was done using the indicator bromocresol green, the volume of NaOH solution required for the titration was 23.1 milliliter. And when the titration was repeated using phenolphthalein indicator, the volume of NaOH required was 46.8 milliliter. The value of N depends upon the number of H plus ion furnished by H3PO4, which in turn depends upon the basicity of H3PO4 or the valency factor of H3PO4. Therefore, the value of N is equal to the basicity of H3PO4 or the valency factor of H3PO4. Now, equivalence of H3PO4 will be equal to equivalence of NaOH. That is, equivalence of H3PO4 is equal to equivalence of NaOH. And equivalence of H3PO4 will be equal to molarity of H3PO4, that is 0.107 m, into volume of H3PO4 in liters, that is 25, divided by 1000 liters, into valency factor of H3PO4, let it be N, and this is equal to equivalence of NaOH. Equivalence of NaOH will be equal to molarity of NaOH, that is 0.115 m, into volume of NaOH in liters, that is 23.1 divided by 1000 liter, into valency factor of NaOH, that is 1. Solving this equation, the value of N is equal to 1. Therefore, when bromocresol green is used as indicator, value of N is equal to 1. Similarly, when the titration was repeated using phenolphthalein indicator, equivalence of H3PO4 is equal to equivalence of NaOH, and equivalence of H3PO4 will be equal to 0.107 into 25 by 1000 into N, where 0.107 is the molarity of H3PO4 and 25 by 1000 liters is the volume of H3PO4 and N is the valency factor of H3PO4. And this is equal to equivalence of NaOH, and equivalence of NaOH will be equal to 0.115 into 46.8 divided by 1000 into 1, where 0.115 m is the molarity of NaOH solution, 46.8 divided by 1000 is the volume of NaOH in liters, and 1 is the valency factor of NaOH. Solving this equation, the value of N is equal to 2. Therefore, when phenolphthalein is used as indicator, then the value of N is equal to 2. Question 35. 9.8 gram of FeSO4 NH4 whole twice SO4 dot XH2O was dissolved in 250 milliliter of its solution. 20 milliliter of this solution required 20 milliliter of KMnO4 solution containing 3.53 gram of 90% pure KMnO4 dissolved per liter. Calculate X. Now equivalents of FeSO4 dot NH4 whole twice SO4 dot XH2O is equal to weight divided by equivalent weight. Now weight of FeSO4 NH4 whole twice SO4 dot XH2O is 9.8 gram and equivalent weight is equal to molecular weight divided by valency factor. Molecular weight is 284 plus 18x divided by valency factor, that is 1. The valency factor is 1 because when this salt is treated with KMnO4, the iron which is present in +2 state or +2 oxidation state gets oxidized to +3 oxidation state. So change in oxidation number is 1 and number of iron atoms is 1. Therefore, the valency factor is 1. So this is the equivalence of the salt present in 250 milliliter of its solution. Therefore, equivalence of FeSO4 dot NH4 twice SO4 dot XH2O in 250 milliliter of solution is equal to 9.8 divided by 284 plus 18x divided by 1. Therefore, equivalence of FeSO4 dot NH4 whole twice SO4 dot XH2O in 20 milliliter is equal to 9.8 divided by 284 plus 18x by 1 into 20 divided by 250 equivalents. Now the KMnO4 solution contains 3.53 grams of KMnO4, of which only 90% is pure KMnO4. Therefore, weight of KMnO4 is equal to 90 by 100 into 3.53 grams, and this is equal to 0.9 into 3.53 grams. Therefore, equivalence of KMnO4. Now the volume of this KMnO4 solution is 1 liter. Therefore, equivalence of KMnO4 in 1000 milliliters is equal to weight of KMnO4, that is 0.9 into 3.53 grams divided by equivalent weight of KMnO4. The equivalent weight of KMnO4 will be equal to molecular weight of KMnO4, that is 158 divided by valency factor, that is 5. Therefore, equivalence of KMnO4 in 20 milliliter of solution is equal to 0.9 into 3.53 divided by 158 by 5 into 20 divided by 1000 equivalents. Now equivalents of FeSO4 dot NH4 whole twice SO4 dot XH2O will be equal to equivalents of KMnO4. Therefore, we can write 9.8 divided by 284 plus 18x by 1 into 20 divided by 250 is equal to 0.9 into 3.53 divided by 158 by 5 into 20 by 1000. Solving this equation, the value of x is equal to 6. Question 36. 10 milliliter of H2O2 weighs 10.205 gram. The solution was diluted to 250 milliliter, 25 milliliter of which required 35.8 milliliter of a decinormal solution of KMnO4. Calculate the weight in grams of H2O2 in 100 milliliter and also the volume strength of the solution. Equivalent weight of H2O2 will be equal to 34 divided by 2, which is equal to 17. 34 is the molecular weight of H2O2 and 2 is the valency factor. Now let the weight of H2O2 present in the solution diluted to 250 milliliter be W grams. That is 250 milliliters of solution contains W grams of H2O2 or W by 17 equivalents of H2O2. Therefore 25 milliliter of solution will contain W by 17 into 25 divided by 250, and this is equal to W by 17 into 10 equivalents of H2O2. Now this 25 milliliter of H2O2 solution required 35.8 milliliter of decinormal solution of KMnO4. Therefore, equivalents of H2O2 in 25 milliliter, that is W by 17 into 10, is equal to equivalents of KMnO4 solution, and equivalents of KMnO4 solution will be equal to normality of KMnO4 solution, that is 1 by 10, into volume of KMnO4 solution in liters, that is 35.8 divided by 1000 liters. Solving this equation, the value for W is equal to 0.6086 grams. Therefore, in the original diluted 250 milliliter solution, the weight of H2O2 is 0.6086 gram, or it can also be said that 10 milliliter of solution contains 0.6086 gram of H2O2. Therefore, 100 milliliter of solution will contain 0.6086 into 100 divided by 10 grams of H2O2, and this is equal to 6.086 grams of H2O2. Now the volume strength of H2O2 solution is the volume of oxygen produced by 1 volume of H2O2, or the volume of oxygen produced by 1 liter of H2O2 solution. So to find the volume strength of H2O2 solution, first we need to find the number of equivalents of H2O2 present in 1 liter of H2O2. Now 100 milliliter of H2O2 contains 6.086 grams of H2O2, or 6.086 divided by 17 equivalents of H2O2. Therefore, 1000 milliliter of H2O2 or 1 liter of H2O2 solution contains 6.086 divided by 17 into 1000 by 100 equivalents of H2O2, or this is equal to 3.58 equivalents of H2O2. Now the equivalents of H2O2 will be equal to the equivalents of oxygen produced. Therefore 3.58 will be equal to equivalents of oxygen produced, and equivalents of oxygen produced will be equal to volume of oxygen produced, let it be X liters, divided by equivalent volume of oxygen, that is 5.6 liters. Solving this, the value of X is equal to 20 liters, or we can say that volume strength of the solution is equal to 20 volumes. Question 37. 50 milliliter of H2O2 was treated with excess of potassium iodide in presence of dilute sulfuric acid. Iodine soliberated was titrated with 20 milliliter of 0.1 N hypo solution. Calculate the strength of H2O2 in grams per liter. The equation for the reaction will be potassium iodide plus H2O2 plus H2SO4 forming K2SO4 plus H2O plus iodine. Now this iodine which is liberated will react with hypo solution. The equation will be Na2S2O3 plus iodine forming NaI plus Na2S4O6. As can be seen from the equation, equivalence of H2O2 is equal to equivalence of iodine, and equivalence of iodine will be equal to equivalence of hyposolution. Now the volume of H2O2 taken is 50 milliliter. Since the volume is in milliliters, the number of milli-equivalents of H2O2 will be equal to number of milli-equivalents of hyposolution, or equivalence of H2O2 in 50 by 1000 liters will be equal to equivalence of Na2S2O3. Now equivalence of Na2S2O3 will be equal to normality of Na2S2O3, that is 0.1 N, into volume of the hyposolution in liters, that is 20 divided by 1000 liters. Now from this we can calculate the equivalence of H2O2 in 1 liter or 1000 milliliter. Therefore, equivalence of H2O2 in 1 liter is equal to 0.1 into 20 by 1000 into 1000 by 50, and this is equal to 0.04 equivalents. Therefore, equivalence of H2O2 in 1 liter is equal to 0.04 equivalents. Therefore, weight of H2O2 in 1 liter is equal to equivalence of H2O2, that is 0.04 equivalents, into equivalent weight of H2O2. The equivalent weight of H2O2 is 17, and this is equal to 0.68 grams. Therefore, strength of H2O2 in grams per liter will be equal to 0.68 grams per liter. Question 38. Calculate the percentage of available chlorine in a sample of 3.546 gram of bleaching powder which was dissolved in 100 milliliter of water. 25 milliliter of this solution on treatment with potassium iodide and dilute acid required 20 milliliter of 0.125 N sodium thiosulfate solution. Now bleaching powder, that is CaOCl, Cl, when treated with potassium iodide will liberate iodine and chlorine gas. Now this iodine on treatment with sodium thiosulfate, that is Na2S2O3, will form Na2S4O6 plus NaI. Now as can be seen from the equation for the reaction, equivalence of bleaching powder will be equal to equivalence of iodine, and equivalence of iodine will be equal to equivalence of chlorine, and equivalence of iodine is also equal to equivalence of sodium thiosulfate. Or it can also be said that equivalence of chlorine is equal to equivalence of sodium thiosulfate. Now the volume of the bleaching powder solution taken is 25 milliliter. Now equivalence of chlorine in 25 by 1000 liters of solution is equal to equivalence of sodium thiosulfate. Equivalence of sodium thiosulfate will be equal to normality of sodium thiosulfate, that is 0.125 N, into volume of sodium thiosulfate in liters, that is 20 divided by 1000 liters. And from this, the equivalence of chlorine in 100 by 1000 liters of solution will be equal to 0.125 into 20 by 1000 into 1000 divided by 25 into 100 by 1000, and this is equal to 1 by 100 equivalents. Now we know the equivalents of chlorine. Therefore, weight of chlorine will be equal to equivalence of chlorine, that is 1 by 100, into equivalent weight of chlorine. Now equivalent weight of chlorine will be equal to molecular weight of chlorine, that is 71, divided by valency factor of chlorine, that is 2, and this is equal to 0.355 gram. Therefore percentage of chlorine will be equal to 0.355 gram divided by weight of the bleaching powder, that is 3.546 gram into 100, and this is equal to 10.01%. Question 39, A part. A zinc rod weighing 25 gram was kept in 100 milliliter of 1 m copper sulfate solution. After a certain time, molarity of Cu2 plus ion in solution was 0.8 m. What was the molarity of the sulfate ion? What was the weight of the zinc rod after cleaning? B part. If the above experiment was done with a copper rod of weight 25 gram and 50 milliliter of 2 m zinc sulfate solution, what would be the molarity of Zn2 plus ions at the end of the same interval? Zinc is more reactive than copper, so zinc will displace copper from copper sulfate. Therefore, zinc plus Cu2 plus ion will form Zn2 plus ions plus copper. As can be seen, zinc is in 0 oxidation state and it gets oxidized to +2 oxidation state. So change in oxidation number of zinc is 2. Number of zinc atoms is 1. Therefore, valency factor of zinc is 2. And equivalence of zinc will be equal to atomic weight of zinc, that is 65.4, divided by valency factor, that is 2. Now Cu2 plus ions change into copper atoms. The oxidation state of copper changes from +2 to 0. So change in oxidation number is 2. Number of copper atoms is 1. Therefore valency factor is 2. Now initially the molarity of copper sulfate solution is 1 m, or the molarity of Cu2 plus ions present is 1 m. Therefore equivalence of Cu2 plus ions present initially will be molarity into volume into valency factor, which is equal to 1 into volume of copper sulfate solution in liters will be 100 divided by 1000 into valency factor of copper, that is 2, and this is equal to 0.2 equivalents. Now after a certain time, after the reaction, the molarity of Cu2 plus ions in solution was 0.8 m. Therefore equivalence of Cu2 plus ions present in the solution after the reaction was molarity, that is 0.8, into volume of solution in liters, that is 100 divided by 1000 into valency factor, that is 2, and this is equal to 0.16 equivalents. Now the equivalence of zinc that changed from zinc to Zn2 plus ions is same as the equivalence of copper that changed from Cu2 plus ions to copper. Now equivalence of copper that changed from Cu2 plus ions to copper will be equal to equivalence of copper ions present initially in the solution, that is 0.2 equivalents, minus equivalence of copper ions present after the reaction, that is 0.16 equivalents, and this is equal to 0.04 equivalents. Therefore, equivalence of zinc that changed into Zn2 plus ions is 0.04 equivalents. Therefore, weight of zinc that changed from zinc to Zn2 plus ions will be equal to equivalence of zinc, that is 0.04 equivalents, into equivalent weight of zinc, that is 65.4 divided by 2, and this is equal to 1.308 gram. So 1.308 grams of zinc changed to Zn2 plus ions. Therefore, weight of zinc rod after the reaction will be 25 minus 1.308, and this is equal to 23.692 grams. Now sulfate ions do not participate in the reaction. Therefore, molarity of sulfate ions in the solution remain the same, that is 1m. Now in the B part of the question, since copper is less reactive than zinc, copper will not displace zinc from its salt, and therefore no reaction will take place, and the molarity of zinc sulfate remains the same, that is 2m. Question 40. 25 milliliter of a mixed solution of sodium carbonate and NaHCO3 required 12 milliliter of N by 20 HCl when titrated using phenolphthalein as an indicator, but 25 milliliter of the same when titrated separately with methyl orange required 30 milliliter of N by 20 HCl. Calculate the amount of Na2CO3 and NaHCO3 in grams per liter. When the titration is done using phenolphthalein as indicator, the reaction will be Na2CO3 plus HCl forming NaHCO3 plus NaCl. Now equivalents of sodium carbonate that reacted with HCl will be equal to the equivalents of HCl. Therefore, equivalents of sodium carbonate will be equal to equivalents of HCl, and equivalents of HCl will be equal to normality of HCl, that is 1 by 20, into volume of HCl in liters, that is 12 by 1000 liters, and this is equal to 0.0006 equivalents. This is the equivalent of sodium carbonate present in 25 milliliter of solution. Therefore, equivalents of sodium carbonate in 25 milliliter is equal to 0.0006 equivalents, and equivalents of sodium carbonate in 1000 milliliter will be equal to 0.0006 divided by 25 into 1000 equivalents, and from this weight of sodium carbonate in 1000 milliliter will be equal to equivalents of sodium carbonate, that is 0.0006 divided by 25 into 1000 into equivalent weight of sodium carbonate, that is 106. Solving this, the weight of sodium carbonate in 1000 milliliter or 1 liter of solution will be equal to 2.544 gram. Therefore, amount of sodium carbonate present in 1 liter of solution is 2.544 gram. Now when the titration is done with methyl orange, then the reaction will be Na2CO3 plus HCl forming NaHCO3 plus NaCl. This NaHCO3 produced will again react with HCl forming NaCl plus H2O plus CO2. NaHCO3 is also present in the mixture. HCl will also react with NaHCO3 present originally in the mixture, and the reaction will be NaHCO3 plus HCl forming NaCl plus H2O plus CO2. Therefore, equivalents of sodium carbonate present in the solution plus equivalents of NaHCO3 formed from sodium carbonate plus equivalents of NaHCO3 which is present originally in the mixture will be equal to equivalents of HCl used up in the reaction. Therefore, it can be written equivalents of sodium carbonate present in the mixture which is equal to 0.0006 equivalents plus equivalents of NaHCO3 formed from sodium carbonate. It will also be equal to 0.0006 equivalents plus equivalents of NaHCO3 present originally in the mixture. That is equivalents of NaHCO3 which is present originally in the mixture is equal to equivalents of HCl. The equivalence of HCl is equal to normality of HCl, that is 1 by 20, into volume of HCl in liters, that is 30 by 1000 liters. Now solving this equation, equivalence of NaHCO3 present originally in the mixture is equal to equivalence of HCl used up in the reaction, that is 0.0015 equivalents, minus 0.0012. This 0.0012 equivalents is the sum of sodium carbonate present in the solution and NaHCO3 produced from sodium carbonate in the solution, and this is equal to 0.0003 equivalents. This is the equivalent of NaHCO3 present in 25 milliliter of solution. Therefore, equivalent of NaHCO3 in 25 milliliter of solution will be equal to 0.0003 equivalents, and equivalents of NaHCO3 in 1000 milliliter of solution will be equal to 0.0003 divided by 25 into 1000 equivalents, and from this weight of NaHCO3 in 1000 milliliter will be equal to 0.0003 divided by 25 into 1000 into equivalent weight of NaHCO3, that is 84. Solving this, weight of NaHCO3 in 1000 milliliter of solution or weight of NaHCO3 in 1 liter is equal to 1.008 grams. Question 41. 20 milliliter of a mixed solution of sodium carbonate and sodium hydroxide required 17.5 milliliter of N by 10 HCl when titrated with phenolphthalein as indicator. But when methyl orange was added, a second endpoint was observed on the further addition of 2.5 milliliter of HCl. Calculate the amount of sodium carbonate and sodium hydroxide in the solution. When phenolphthalein is used as indicator, the reaction is NaOH plus HCl forming NaCl plus H2O and Na2CO3 plus HCl forming NaHCO3 plus NaCl. The equivalents of NaOH plus equivalents of Na2CO3 will be equal to equivalents of HCl. That is equivalents of NaOH plus equivalents of Na2CO3 will be equal to equivalents of HCl, and equivalents of HCl is equal to normality of HCl, that is 1 by 10 into volume of HCl in liters, 17.5 divided by 1000 liters, and this is equal to 0.0003 175 equivalents. Now when methyl orange is used as indicator, the reaction is NaHCO3 plus HCl forming NaCl plus H2O plus CO2. The equivalents of NaHCO3 will be equal to equivalents of HCl. Now according to the question, the second endpoint was observed on further addition of 2.5 milliliter of HCl. Therefore, equivalents of NaHCO3 will be equal to equivalents of HCl, and equivalents of HCl will be equal to normality of HCl, that is 1 by 10, into volume of HCl in liters, that is 2.5 divided by 1000 liters, and this is equal to 0.00025 equivalents. Now equivalents of NaHCO3 will be equal to equivalents of sodium carbonate. Therefore, putting the value of equivalents of sodium carbonate, we get equivalents of NaOH is equal to 0.00175 minus equivalents of sodium carbonate, that is 0.00025 equivalents, and this is equal to 0.0015 equivalents. Therefore, equivalents of NaOH is 0.0015 equivalents. From this, weight of NaOH is equal to equivalents of NaOH, that is 0.0015 equivalents, into equivalent weight of NaOH, that is 40, and this is equal to 0.06 grams. Therefore, weight of NaOH present is 0.06 grams. Now, equivalents of sodium carbonate is equal to equivalents of NaHCO3, which is equal to 0.00025 equivalents. Therefore, equivalents of Na2CO3 is equal to 0.00025 equivalents. Therefore, weight of Na2CO3 is equal to equivalents of Na2CO3, that is 0.00025 equivalents, into equivalent weight of Na2CO3, that is 106, and this is equal to 0.0265 grams. Therefore, weight of sodium carbonate is equal to 0.0265 grams. Question 42. 0.2 gram of a chloride of an element was dissolved in water and then treated with excess of silver nitrate solution, resulting in the formation of 0.47 gram of silver chloride. Find the equivalent weight of the element. The equivalents of chloride of the element will be equal to equivalents of AgCl formed. Equivalent of chloride can be written as weight of chloride, that is 0.2 gram, divided by equivalent weight of chloride. Equivalent weight of AgCl will be equal to weight of AgCl, that is 0.47, divided by equivalent weight of AgCl, and equivalent weight of AgCl is 143.5. Now from this, equivalent weight of chloride will be equal to 61.06. Now equivalent weight of the chloride will be equal to equivalent weight of the element plus equivalent weight of chlorine. Therefore, equivalent weight of the element will be equal to equivalent weight of the chloride, that is 61.06, minus equivalent weight of chlorine, that is 35.5, and this is equal to 25.56. Therefore, equivalent weight of the element is equal to 25.56. Question 43. A sample of hydrogen sulfate was dissolved in 100 milliliter of water. 10 milliliter of this solution was reacted with the excess of ferric chloride solution and warmed to complete the reaction. Ferrous ion formed was estimated and it required 20 milliliter of M by 50 potassium permanganate solution. Estimate the amount of hydrogen sulfate in 1 liter of the solution. The reaction is given here. As can be seen from the chemical equation, equivalents of hydrogen sulfate will be equal to equivalents of Fe2 plus ions, and equivalents of Fe2 plus ions will be equal to equivalents of KMnO4 solution. The formula for hydrogen sulfate is N2H6SO4. Molecular weight of hydrogen sulfate is equal to 130. Equivalent weight of hydrogen sulfate is equal to 130, that is molecular weight, divided by 4. 4 is the valency factor and this is equal to 32.5. As can be seen from the chemical reaction, the oxidation number of nitrogen atom changes by 2. Therefore, the total change in oxidation number of 2 nitrogen atoms will be 4. Therefore, valency factor is 4. And equivalent weight of hydrogen sulfate is 130 divided by 4, that is equal to 32.5. Now, equivalents of hydrogen sulfate, that is N2H6SO4, is equal to equivalents of KMnO4, and equivalents of KMnO4 will be equal to molarity of KMnO4, that is 1 by 50, into volume of KMnO4 in liters, that is 20 divided by 1000 liters, into valency factor of KMnO4, that is 5. Solving this, the equivalents of hydrogen sulfate is equal to 0.002 equivalents. Now 10 milliliter of solution of hydrogen sulfate contains 0.002 equivalents of hydrogen sulfate. Therefore, 1000 milliliters of solution or 1 liter of solution will contain 0.002 divided by 10 into 1000 equivalents of hydrogen sulfate, and therefore weight of hydrogen sulfate, that is N2H6SO4, in 1 liter of solution will be equal to equivalents of hydrogen sulfate in 1 liter of solution, that is 0.002 divided by 10 into 1000 into equivalent weight of hydrogen sulfate, that is 32.5. Solving this, the weight of hydrogen sulfate in 1 liter of solution will be equal to 6.5 grams. Question 44. 5 gram of bleaching powder was suspended in water and volume made up to half a liter. 20 milliliter of this suspension, when acidified with acetic acid and treated with excess of potassium iodide solution, liberated iodine, which required 20 milliliter of a N by 10 hypo solution for titration. Calculate the percentage of available chlorine in bleaching powder. The equivalent of available chlorine in bleaching powder is equal to equivalent of iodine, which is liberated, which is equal to equivalence of hypo solution. Therefore, equivalent of chlorine is equal to equivalent of hypo solution, and equivalent of hypo solution will be equal to normality of hypo solution, that is 1 by 10, into volume of hypo solution in liters, that is 20 divided by 1000 liters, and this is equal to 0.002 equivalents. Now this is the equivalent of chlorine present in 20 milliliter of the suspension. Therefore, 20 milliliter of bleaching powder suspension contains 0.002 equivalents of chlorine, and 500 milliliters of bleaching powder suspension will contain 0.002 divided by 20 into 500 equivalents of chlorine. From this, weight of chlorine will be equal to equivalents of chlorine, that is 0.002 divided by 20 into 500 into equivalent weight of chlorine, that is 35.5. And from this, percentage of chlorine will be equal to weight of chlorine, that is 0.002 divided by 20 into 500 into 35.5 divided by weight of bleaching powder, that is 5 gram, into 100. Solving this, the percentage of chlorine is 35.5%. Question 45. A 10-gram mixture of Cu2S and CuS was treated with 200 milliliter of 0.75 m MnO4 minus in acid solution producing sulfur dioxide, Cu2 plus and Mn2 plus. The sulfur dioxide was boiled off and the excess MnO4 minus was titrated with 175 milliliter of 1m Fe2 plus solution. Calculate the percentage of CuS in the original mixture. The mixture of Cu2S and CuS reacts with MnO4 minus to form Cu2 plus ion plus sulfur dioxide plus Mn2 plus. In Cu2S, the oxidation number of copper is +1, sulfur is -2. When this Cu2S changes to Cu2 plus, the oxidation number of each copper atom changes by 1. Therefore, oxidation number of two copper atoms will change by 2, and oxidation number of sulfur changes from -2 to +4 in SO2. Therefore, change in oxidation number of sulfur is 6. Therefore, in Cu2S, the total change in oxidation number of copper and sulfur is 2 plus 6, and this is equal to 8. Therefore, equivalent weight of Cu2S will be molecular weight of Cu2S, that is 159 divided by 8. In CuS, the oxidation number of copper is +2, oxidation number of sulfur is -2, and the change in oxidation number of sulfur is from -2 to +4, and there is no change in the oxidation number of copper. Therefore, the change in oxidation number for CuS is 6. Therefore, equivalent weight of CuS is molecular weight, that is 95.5 divided by 6. Now let the weight of Cu2S in the mixture be x grams and the weight of CuS in the mixture will be 10 minus x grams. Now equivalents of MnO4 minus used will be equal to equivalents of MnO4 minus present, which is equal to molarity of MnO4 minus, that is 0.75 into volume in liters, that is 200 divided by 1000 liters into valency factor, that is 5, minus equivalents of MnO4 minus left after the reaction, which is equal to equivalents of Fe2 plus ion. And equivalents of Fe2 plus ion will be molarity of Fe2 plus ion solution, which is 1 into volume of solution in liters, that is 175 divided by 1000 liters into valency factor, which is 1. Solving this, equivalents of MnO4 used is equal to 0.575 equivalents. Equivalents of MnO4 minus used is equal to 0.575 equivalents. Now equivalents of Cu2S, that is equivalents of Cu2s plus equivalents of Cus will be equal to equivalents of MnO4 minus used in the reaction, that is 0.575 equivalents. Now equivalents of Cu2s will be equal to weight of Cu2s, that is x gram, divided by equivalent weight of Cu2s, that is 159 by 8, plus equivalents of Cus. Equivalents of Cus will be equal to weight of Cus, that is 10 minus x gram, divided by equivalent weight of Cus, that is 95.5 by 6, and this is equal to 0.575. Solving this equation, the value for x is equal to 4.26 grams. Therefore, weight of Cus is equal to 10 minus 4.26, which is equal to 5.74 grams. Therefore, percentage of Cus in the mixture is equal to weight of Cus, that is 5.74 grams, divided by total weight of the mixture, that is 10 grams, into 100, and this is equal to 57.4%. Question 46. A 0.518 gram sample of limestone is dissolved and then calcium is precipitated as CaC2O4. After filtering and washing the precipitate, it requires 40 ml of 0.25 N KMnO4 solution acidified with H2SO4 to titrate it. What is the percentage of calcium oxide in limestone? The equation is given here. This is the given equation for the reaction. Now, as can be seen from the equation, equivalents of CaC2O4 is equal to equivalents of KMnO4. Now, calcium carbonate on heating decomposes to form calcium oxide plus carbon dioxide. Now, equivalents of calcium carbonate will be equal to equivalents of calcium oxide, and equivalents of calcium carbonate will also be equal to equivalents of CaC2O4, and equivalents of CaC2O4 will be equal to equivalents of KMnO4. Or it can also be said that equivalents of calcium oxide is equal to equivalents of KMnO4. Therefore, equivalents of calcium oxide is equal to equivalents of KMnO4, and equivalents of KMnO4 will be equal to normality of KMnO4, that is 0.25 N into volume of KMnO4 in liters, that is 40 divided by 1000 liters. Solving this, the equivalents of calcium oxide is equal to 1 by 100 equivalents. Therefore, weight of calcium oxide will be equal to equivalents of calcium oxide, that is 1 by 100, into equivalent weight of calcium oxide, which is equal to 56 divided by 2. 56 is the molecular weight of calcium oxide and 2 is the valency factor. And this is equal to 0.28 grams. Now from this, percentage of calcium oxide will be equal to weight of calcium oxide, that is 0.28 grams, divided by weight of limestone, that is 0.518 grams into 100, and this is equal to 54.1%. Question 47. 20 milliliter of M by 60 solution of KbRO3 was added to a certain volume of SeO3 2- solution. Bromine evolved was removed by boiling and excess of KbRO3 was back titrated with 5.1 milliliter of M by 25 solution of NaAsO2. Calculate the weight of SeO3 2- in the solution. Now in this question, moles of KbRO3 which is present initially can be calculated from the molarity of the solution, that is M by 60, and volume of the solution, that is 20 milliliters. Now the equations are given, and initially some amount of KbRO3 reacts with SeO3 2- and excess of KbRO3 is back titrated using 5.1 milliliter of m by 25 NaSO2 solution. Therefore, we can write moles of KbRO3 present is equal to molarity of KbRO3 solution, that is 1 by 60, into volume of KbRO3 solution in liters, that is 20 by 1000 liters, and this is equal to 1 by 3000 moles. Now in the first equation, the oxidation number of bromine changes from plus 5 to 0, and number of bromine atoms in BrO3 minus is 1. Therefore, change in oxidation number is 5 and valency factor is 5. Now from this equation, it can be seen that equivalence of BrO3 minus is equal to equivalence of SeO3 2 minus, and equivalence of BrO3 minus will be equal to 5 into, where 5 is the valency factor, moles of BrO3 minus used in the reaction, and this is equal to equivalence of SeO3 2 minus. Now how to calculate the excess of KbRO3? Now in the second equation, the oxidation number of bromine changes from plus 5 to minus 1. The change in oxidation number is 6 and the number of bromine atoms in BrO3 minus is 1. Therefore, valency factor is 6. Therefore, equivalence of BrO3 minus, which is in excess, is equal to valency factor of BrO3 minus in the second equation, that is 6 into moles of BrO3 minus in excess, and this is equal to equivalence of AsO2 minus. Now in the second equation, the oxidation number of arsenic changes from plus 3 to plus 5. Therefore, change in oxidation number of arsenic is 2 and number of arsenic atoms in AsO2 minus is 1. Therefore, valency factor is 2. Therefore, equivalence of AsO2 minus can be written as valency factor, that is 2 into moles of AsO2 minus. Now moles of AsO2 minus will be equal to 2 into molarity of NaSO2 solution, that is 1 by 25, into volume of NaSO2 solution in liters, that is 5.1 divided by 1000 liters. Now from this equation, moles of BrO3 minus in excess will be equal to 2 by 6 into 1 by 25 into 5.1 divided by 1000. This is equal to 1.7 divided by 25 into 1000 moles. Now subtracting the moles of KbRO3 present in excess from the moles of KbRO3 present initially, we get the moles of KbRO3 used in the reaction. Moles of KbRO3 used in the reaction will be equal to moles of KbRO3 present, that is 1 by 3000, minus moles of KbRO3 present in excess, that is 1.7 divided by 25 into 1000, and this is equal to 0.000265 moles. Now from this, equivalence of SeO3 2 minus is equal to 5 into moles of KbRO3 used in the reaction, that is 0.000265. Therefore, 5 into 0.000265 will give the equivalence of SeO3 2 minus. And from this, weight of SeO3 2 minus will be equal to equivalence of SeO3 2 minus, that is 5 into 0.000265 into equivalent weight of SeO3 2 minus, that is 127 divided by valency factor, that is 2, and this is equal to 0.084 grams. Question 48. Concentrated HCl solution is 37% HCl and has density of 1.19 gram per milliliter. A dilute solution of HCl is prepared by diluting 4.50 milliliter of this concentrated HCl solution to 100 milliliter with water. Then 10 ml of this dilute HCl solution reacts with an AgNO3 solution. Calculate the volume of 0.108 m AgNO3 solution required to precipitate all the chloride as AgCl solid. The HCl solution is 37% HCl. This 37% can also be written as 37 by 100. Therefore, volume of HCl is 37 milliliter and volume of the solution is 100 milliliter. Therefore, moles of HCl will be equal to weight of HCl. Now, how to get the weight of HCl? Weight of HCl will be equal to volume into density, that is 37 into 1.19, and weight of HCl divided by its molecular weight, that is 36.5, will give the moles of HCl. Now we know the moles of HCl. From this we can find out the molarity of the given HCl solution. This is equal to moles of HCl, that is 37 into 1.19 divided by 36.5 moles divided by volume of solution in liters. Now volume of solution of HCl is 100 milliliter. Therefore, dividing the moles of HCl by volume of solution in liters, that is into 100 into 1000. This will give the molarity of the given HCl solution. Solving this, the molarity of HCl solution is 12.06 m. Now this is the molarity of the given HCl solution. 4.5 ml of this solution is diluted with water, and the new solution has the volume 100 milliliter. Therefore, applying the formula M1V1 is equal to M2V2, we can get the molarity of the new solution. Now here M1 is equal to 12.06 into V1 is equal to 4.5 milliliter, or 4.5 divided by 1000 liters, and this is equal to M2 into the new volume is 100 milliliter, or 100 by 1000 liters. Solving this, the molarity of the solution, 100 ml solution, will be equal to 0.5427 m. Now the solution of HCl having molarity 0.5427 is treated with AgNO3 solution. Now milliequivalents of HCl will be equal to milliequivalents of AgNO3 solution. Now milliequivalents of HCl will be equal to valency factor of HCl, that is 1, into molarity of HCl, that is 0.5427, into volume of HCl, that is 10 milliliters, and this is equal to milliequivalents of AgNO3, which is equal to valency factor of AgNO3, that is 1, into molarity of AgNO3 solution, that is 0.108 m, into volume of AgNO3 solution, let it be V. Solving this, the volume of AgNO3 solution is equal to 50.25 milliliters. Question 49. 0.9546 gram of Rochelle salt on ignition gave sodium potassium carbonate, which was treated with 41.72 milliliter of 0.1307 N H2SO4. The unreacted H2SO4 was then neutralized by 1.91 milliliter of 0.1297 N NaOH. Find the percentage purity of the Rochelle salt in the sample. The milliequivalents of H2SO4 present can be obtained by multiplying the normality of H2SO4 solution with volume and the unreacted H2SO4. The milliequivalents of unreacted H2SO4 will be equal to milliequivalents of NaOH. Therefore, milliequivalents of H2SO4 present will be equal to 0.1307, that is normality of H2SO4 solution, into volume of H2SO4 solution, that is 41.72 milliliters, and this is equal to 5.453 milliequivalents. Now milliequivalents of H2SO4 unreacted will be equal to normality of NaOH given as 0.1297, volume of NaOH, that is 1.91 milliliters, and this is equal to 0.248 milliequivalents. Now from this, milliequivalents of H2SO4 reacted will be equal to 5.453, that is milliequivalents of H2SO4 present, minus 0.248, that is milliequivalents of H2SO4 unreacted, and this is equal to 5.205 milliequivalents. Now milliequivalents of H2SO4 reacted will be equal to milliequivalents of sodium potassium carbonate, which in turn will be equal to milliequivalents of the Rochelle salt. Therefore, milliequivalents of salt is equal to 5.205 milliequivalents. From this, weight of salt will be equal to equivalents of the salt, that is 5.205 divided by 1000 equivalents. To change milliequivalents into equivalents, we will have to divide the milliequivalents by 1000. Therefore, weight of salt will be equal to 5.205 divided by 1000 equivalents into equivalent weight of the salt. Now, equivalent weight of the salt will be equal to molecular weight of the salt, that is 282, divided by valency factor, that is 2. Solving this, the weight of the salt is equal to 0.7339 gram. Therefore, percentage purity of the salt in the sample is equal to weight of the pure salt, that is 0.7339 gram, divided by total weight of the salt, that is 0.9546 gram into 100, and this is equal to 76.88%. Question 50. A mixture of KMnO4 and K2Cr2O7 weighing 0.24 gram on being treated with Ki in acid solution liberates just sufficient iodine to react with 60 milliliter of 0.1 N Na2S2O3 solution. Calculate percentage of chromium and manganese in the mixture. Now in this question, we need to calculate the percentage of chromium and manganese in the mixture. Now equivalence of the hypo solution or Na2S2O3 solution will be equal to equivalence of iodine, and equivalence of iodine will be equal to the sum of equivalents of KMnO4 and K2Cr2O7. Now let the weight of KMnO4 present in the mixture be x gram, and weight of K2Cr2O7 present in the mixture will be 0.24 minus x gram. Therefore, sum of the equivalents of KMnO4 and equivalents of K2Cr2O7 will be, now the equivalent of KMnO4 will be weight of KMnO4, that is x gram, divided by equivalent weight of KMnO4, that is 158 by 5, where 158 is the molecular weight of KMnO4 and 5 is the valency factor, plus equivalents of K2Cr2O7 in the mixture will be 0.24 minus x, that is weight of K2Cr2O7, divided by equivalent weight of K2Cr2O7. Now equivalent weight of K2Cr2O7 will be molecular weight of K2Cr2O7, that is 294, divided by valency factor, that is 6, and this is equal to equivalence of iodine, which in turn is equal to equivalence of Na2S2O3 solution. Now equivalence of Na2S2O3 solution will be normality of Na2H2O3 solution, that is 0.1 N, into volume of Na2H2O3 solution in liters, that is 60 by 1000 liters. Solving this equation, the value of X is equal to 0.098 grams. Therefore, weight of KMnO4 in the mixture is 0.098 grams and weight of K2Cr2O7 in the mixture will be 0.24 minus 0.098, which is equal to 0.142 grams. Now percentage of manganese in the mixture will be equal to, the molecular weight of KMnO4 is 158 and one molecule of KMnO4 contains only one atom of manganese. Therefore, out of 158, amount of manganese present is 55, and multiplying this by 0.098 will give the amount of manganese present in 0.098 grams of KMnO4, and dividing it by 0.24 grams, that is the weight of the mixture, will give the amount of manganese present in 0.24 gram of the mixture, and multiplying this by 100 will give the percentage of manganese, which is equal to 14.21%. Similarly, percentage of chromium in the mixture will be equal to, the molecular weight of K2Cr2O7 is 294 and the number of chromium atoms in one molecule of K2Cr2O7 is 2. Therefore, out of 294, 104. This is the weight of 2 chromium atoms. Therefore, when the weight of K2Cr2O7 is 294, the weight of chromium present is 104. Multiplying this by 0.142 grams will give the weight of chromium present in 0.142 grams of K2Cr2O7, and dividing this by 0.24 grams will give the weight of chromium in 0.24 grams of the mixture, and multiplying this by 100 will give the percentage of chromium, which is equal to 20.9%. Question 51. Federal regulations set up an upper limit of 50 parts per million of ammonia in the air in a work environment, that is 50 milliliter ammonia per 10 to the power 6 milliliter of air. The density of ammonia at room temperature is 0.771 gram per liter. Air from a manufacturing operation was drawn through a solution containing 100 milliliter of 0.0105 m HCl. The ammonia reacts with HCl as follows: ammonia plus HCl forming ammonium chloride. After drawing air through the acid solution for 10 minutes at a rate of 10 liters per minute, the acid was titrated. The remaining acid required 13.1 milliliter of 0.0588 m NaOH to reach the equivalence point. A part: how many grams of ammonia were drawn into the acid solution? B part: how many parts per million of ammonia were in the air? C part: is this manufacturer in compliance with regulations? Now, milliequivalents of ammonia will be equal to milliequivalents of HCl, or equivalents of ammonia will be equal to equivalents of HCl, which is used up in the reaction with ammonia. Now, equivalents of HCl used up in this reaction will be equal to equivalents of HCl present at the beginning of the reaction minus equivalents of HCl which is left at the end of the reaction. Now, equivalents of HCl which is left at the end of the reaction will be equal to equivalence of NaOH. The amount of air which is drawn through the acid solution in 10 minutes will be 10 into 10, that is 100 liters. Now solving this question, first equivalence of HCl present is equal to molarity of HCl, that is 0.0105 m, into volume of HCl in liters, that is 100 by 1000 liters, into valency factor of HCl, that is 1, and this is equal to 0.00105 equivalents. Now equivalents of HCl remaining after the reaction will be equal to equivalents of NaOH, and equivalents of NaOH will be equal to molarity of NaOH, that is 0.0588 m, into volume of NaOH, that is 13.1 divided by 1000 liters, into valency factor of NaOH, that is 1, and this is equal to 0.00077028 equivalents. Therefore, equivalents of ammonia will be equal to equivalents of HCl present minus equivalents of HCl remaining, that is 0.00105 minus 0.00077028, and this is equal to 0.0002797 equivalents. Now from this, weight of ammonia will be equal to equivalents of ammonia, that is 0.0002797 into equivalent weight of ammonia, that is 17, and this is equal to 0.00475 gram. Therefore, the answer to the first part of the question is 0.00475 gram. Now the B part, how many parts per million of ammonia were in the air? Now in 1 minute, amount of air that was drawn is 10 liters. Therefore, in 10 minutes, the amount of air drawn will be equal to 10 into 10, which is equal to 100 liters, and this is also equal to 100 into 1000 milliliters. Now weight of ammonia is equal to 0.00475 gram. Density of ammonia is equal to 0.771 grams per liter. Therefore, volume of ammonia will be equal to mass by density, that is 0.00475 divided by 0.771, and this is equal to 0.00616 liters, and this is also equal to 0.00616 into 1000 milliliters. Therefore, the volume of ammonia in 100 into 1000 milliliter of air is 0.00616 into 1000 milliliter. That is, volume of ammonia in 100 into 1000 milliliter of air is 0.00616 into 1000 milliliters. Therefore, volume of ammonia in 10 to the power 6 milliliters of air will be 0.00616 into 1000 divided by 100 into 1000 into 10 to the power 6. Solving this, the value is equal to 61.6 milliliter. Therefore, in 10 to the power 6 milliliter of air, the amount of ammonia present is 61.6 milliliter, or it can also be said that amount of ammonia present in air is 61.6 parts per million. Now, the C part of the question, is this manufacturer in compliance with regulation? The answer is no, because the amount of ammonia which is allowed is 50 parts per million, but amount of ammonia present is 61.6 parts per million. Therefore, answer is no.